In Jorithang, a city in South Sikkim, farmers face harsh summers and water scarcity that reduces yields and water resources. AgroSmart changes this. A sensor based smart irrigation system with rainwater harvesting and crop intelligence. It saves water, boosts productivity, and gives farmers reliable automated control. Now, we'll explain our solution.
You can see the soil moisture sensor and the humidity and temperature sensor is sending values to the ESP32, which is in turn publishing the values to the website using Wi-Fi, and it is getting updated to the Arduino IDE.
This is AgroSmart, an interface between our hardware solution and farmers of Sikkim. This is the registration page and the sign in page, which is fully connected to the backend server. This is the dashboard, which shows general information about a farmer's farm and other updates. A farmer's field is divided into 9 zones, each with an ESP giving continuous data. Once the soil moisture sensor shows a value below 30%, a signal is sent to the 4x3 solenoid valve via the master ESP. This enables the field to be irrigated.
When our sensors detect a lack of moisture in the soil, an automated SMS will be sent by a server informing the farmer of this.
As you can see, the sensor data is being sent to the website along with an ESP zone tag to identify which zone is sending the data. Based on the feedback from the sensors, we can identify which zone needs irrigation and send the signal from the master ESP.
Next, we have Irrigation AI. It is connected to the crop database that determines optimal watering levels and other analytics based on the valve's mechanical dimensions and pressure. Here we see tobacco, and next we can check for another crop like maize, which are common crops grown in Sikkim. Next is the analytics, which shows data published by the ESP. It refreshes every 10 seconds so the farmer is up to date with information about his field.
To implement communication over large acres of land where network access may be limited, we have set up a mesh network of ESP32s. The farm is divided into zones, with each zone containing an ESP32 along with a temperature, soil moisture, and atmospheric pressure sensor. By using this, we can monitor which area of the farm needs irrigation and optimize our proportional valve control system accordingly. The ESP32s communicate with each other using the ESP Now protocol, where each ESP can act as the master and the slave. The ESP32s in each grid communicate with each other, passing information along until they reach the master ESP, which is directly connected to the server. From here, the feedback is updated live on our website.
Lastly, we have crop intelligence, which gives a farmer information about ideal crops in various seasons and facts he should keep in mind while sowing a crop.
To demonstrate the working of our proportional valve control system, we are testing on an electric pump setup with solenoid valve for control in a fluids lab. The electric pump is connected to the tank and pressure relief valve, which manages the load of the system when there is too much pressure generated by water. Pressure relief valve is connected in parallel to the rainwater harvesting container, which has one check valve at fixed pressure to allow water to go into the tank when the set amount of water is achieved, and one is connected to the tank, allowing the water to flow when there is a requirement. The command given to the ESP consists of the zone number and the time period for irrigation. The motor is attached to the valve and the ESP is connected to a switching circuit which switches on the valve lines depending on the PWM value. +1 for A line, 0 for no actuations, and -1 for B line. This actuates the hydro motor which rotates clockwise when fluid flows from A to B and anti-clockwise when it flows from B to A. On top of which there is a single outlet sprinkler having a narrow nozzle to increase the pressure of the water which is coming out. This increases the distance each sprinkler covers.